Hi folks, in this module we're going to do some kind of odds and ends. What I want to do is first of all show you, we looked at regions of convergence, and in some sense this is all about regions of convergence. We looked at the fact that if you had a right-sided function you would get a region of convergence that was outside of a circle, and if you had a left-sided function you would get a region of convergence that was inside a circle. And we never talked about two-sided functions, so let's start with that. And then I'll show you a mapping that connects the Laplace transform with the Z transform and some ideas about how to look at spectral properties of discrete functions. Okay, so let's start with a two-sided function. So the two-sided function that we'll use is going to be like our other templates. So here is a to the absolute value of n, and remember, absolute value of n is equal to positive n for n greater than 0 and minus n for n less than 0, right? So if I have a to the n, and let's say a is a number with a magnitude less than 1, then say 0.9, then a to the 0 will be 0.9, a to the 0 will be 1, a to the 1 will be 0.9, a squared will be 0.81, and so on. It's going to be an exponentially decreasing this way. And here, if we pick n equals minus 1, then the absolute value of minus 1 is 1, and then we'll get 0.9 to the 1, which is again the same. So it's a symmetric function, right? If, on the other hand, it has a magnitude greater than 1, say it's 1.5, then a to the power 0 is still 1, but a to the power 1 will be 1.5, and a to the power 2 will be 1.5 squared, and so on. I mean, basically what will happen is you'll get an exponential increase in both directions. Okay, so let's just take a look at this in general. We'll find the Z transform of it and see what happens for different values of a. Okay, so because absolute value of n is equal to n for n greater than 0 and minus n for n less than 0, I can write x of n as a to the power n for n greater than 0 and a to the power minus n for n less than 0. Right? And now let's take the Z transform. So x of z is equal to summation n equals minus infinity to infinity of a to the n u of n plus a to the minus n u of minus n minus 1 z to the minus n. Notice, by the way, this is u of minus n minus 1. It's not u of minus n. And the reason is if I picked u of minus n, I would use the value for n equals 0 twice. If you don't see that, we can talk about it. So then I can take this and break it up. So this is n equals minus infinity to infinity, a to the n u of n z to the minus n plus summation n equals minus infinity to infinity a to the minus n u of minus n minus 1 z to the minus n. And I can do that if everything converges. If things don't converge, I can't do that. So now let me take each one and find out where it converges, and then in the region in which both of them converge, I can add the two up. Okay, so this one I know already. This is our standard n equals 0 to infinity because of u of n, a to the n, z to the minus n, and then this is, again, because if u of minus n minus 1, this will go from minus infinity to minus 1, a to the minus n, z to the minus n. Right, I know what this is. This is, well, let's do the whole thing. Whoops. n equals 0 to infinity. I can write this as a z to the minus 1 to the power n plus summation. And I'm going to do the same thing that I did before, the trick I used before. I'll replace n with minus n. And I can do that as long as I do that over here as well. Here n goes from minus infinity to minus 1. So if I replace n with minus n, then minus n will go from, or n minus n will then go from minus infinity to minus 1, or n will go from infinity to 1. And I can always flip the limits on a summation, something I can't do without multiplying with a minus 1 in case of an integral. But in case of a summation, I can always flip the limits. So this becomes n equals 1 to infinity, and I'll replace a to the minus n with a to the n, and z to the minus n with z to the n. So this will become az to the power n, right? This is now my right-sided sequence here. So this becomes az to the minus 1 to the power 0 minus az to the minus 1, the power goes to infinity, divided by 1 minus az to the minus 1. And here I get az to the n, so this will be az to the power 1, which is just az, minus az, this goes to infinity, the power goes to infinity, over 1 minus az. Right, so this thing now, for this to converge, I have to have az to the minus 1, the magnitude of az to the minus 1 to be less than 1. For this to converge, I have to have the magnitude of az to be less than 1. Okay, so let's figure out what values of z are okay with that. So I have two conditions. For this one, I need az to the minus 1 absolute value to be less than 1. And for this one, I need az to the absolute value to be less than 1. Az to the minus 1 is the same as a over z. I can take z over to the other side, and I get, this means that magnitude of z has to be greater than the magnitude of a, right? Because this thing, az to the minus 1, is the same thing as a over z, and then I can multiply this side by, I can take z over onto this side, and I get z is greater than a, and I wrote it like this. Okay, for this one, I have az is less than 1. Now, if I take a to the other side, I have to divide it. So that means that z is less than 1 over a. So for this to converge, the magnitude of z has to be greater than a. For this to converge, the magnitude of z has to be less than 1 over a. Okay, so let's take two cases where a is greater than 1 and where a is less than 1. Where a is less than 1, let's suppose a is somewhere over here, and this is 1, and this is a, right? Then this says that the region of convergence is outside of this circle, right? And if a is less than 1, then 1 over a will be greater than 1, right? So 1 over a will be out here. And this says that the region of convergence is inside of this circle. So for this term, the region of convergence has to be outside of the circle. For this term, the region of convergence has to be inside the circle. So the region of convergence, the intersection of the two, is this region between the two circles. Okay, so we get x of z then is equal to, let's write this, a to the power 0 is just 1, 1 over 1 minus a z to the minus 1 plus az over 1 minus az. Right? In this region, this annual region. Let's combine these. So this is just z over z minus a plus az over 1 minus az. And if I put them on a denominator, same denominator, I get z minus a times 1 minus az, and this will be z minus az squared plus az squared minus a squared z. Those cancel out, and I'm not so much concerned with what is in the numerator right now, but look at where the poles are. This pole is at z equals a, right here, at z equals a. And here, this thing will go to 0 when 1 minus az is equal to 0, or if 1 minus az is equal to 0, then minus az equals minus 1, and z equals 1 over a. Right? So this is one of the poles, and this is the other pole. So if I have a two-sided sequence, then I'll get the region of convergence that I get is going to be between two circles, and the radius of those circles will be defined by the magnitude of the poles. Okay? Always, the poles always define the boundary of the region of convergence. Okay, so now we have all three cases. If you have a right-sided function, the region of convergence is outside of a circle. If you have a left-sided function, the region of convergence is inside of the circle. And if you have a two-sided function, the region of convergence is between two circles. Okay. Think back to Laplace transform. In the Laplace transform, we had, if you had a right-sided function, the region of convergence was to the right of a line. If you had a left-sided function, the region of convergence was to the left of a line. And if you had a two-sided function, the region of convergence was between two lines. Okay? And let's see if we can map one from one to the other. So that's what we'll do now. We're in the Laplace domain, where we have two axes, sigma and j omega. And here we have the z domain, and we don't have any names, special names for these, so we'll just call it the real part of z and the imaginary part of z. Okay. And what I'm going to do is I'm going to define a mapping that maps from this plane to this plane. And the mapping that I'm going to use is z is equal to e to the s. Right? Or I can write that as e to the sigma plus j omega, or that is e to the sigma times e to the j omega. Oops, no zero here. Okay, so if I pick a point here, that point is going to be defined by a value of sigma, let's call that sigma 0, and a value of omega, let's call that omega 0. That's where this omega 0 came from. And now if I use this mapping, this point here will get mapped to a point. So if I call this point S0, then that will get mapped to a point Z0, which is equal to e to the S0, which is equal to e to the sigma 0, e to the j omega 0. Okay, let's call this R0. Okay, so basically what that is this point S0 gets mapped to a point Z0, and the relationship between those two is that this distance here, R0, is e to the power e to the sigma 0. So this thing is, I've got it too cluttered here, but this is e to the sigma 0, this length, and this angle is omega 0. Right? So this angle is omega 0. That way I can map a point from this plane, the S-plane, the Laplace domain, into the Z domain, into the Z plane. Okay, so that's going to be my mapping. Now notice what happens. If I have a line in the S-plane, and let's suppose this value is sigma 0, right? All points along here, all the points along here have a real part sigma 0, and the imaginary part is omega, and omega can change all over the place, right? So this is the j omega axis, and here is the sigma axis. We fix sigma to be equal to sigma 0, and we let omega change all over the place. Now if I come to this side now, what I have is, here I have S is equal to sigma 0 plus j omega. Then Z will be equal to e to the S, which is equal to e to the sigma 0, e to the j omega. So the distance is fixed at sigma 0, but omega can change all over the place. So if I go over here, real part of Z, imaginary part of Z, all the points Z corresponding to points along this line will have a radius or a distance. This distance will be e to the power sigma 0. But the angle can be anything. The angle can vary all over the place. So what that means is if I take all possible angles, then I end up with a circle. And anywhere on this circle, any point on this circle, the radius is e to the sigma 0 and the angle is some j omega. So if I pick any point here, sigma 0 and omega, it'll land on a point on the circle. So this line here gets mapped into this circle. Okay, so now you can kind of begin to see where in the Laplace domain you have, the region of convergence is always bounded by a line, but in the Z domain, the region of convergence is always bounded by a circle. Lines map into circles. Lines in the S-plane map into circles in the Z domain. Okay, what about the right side of the line and the left side of the line? Well, suppose I pick a point, any point, on the right side of this line. Right? In this point will correspond to some value sigma 1. Sigma 1 is going to be greater than sigma 0. Right? So for any point on the right side of this line, sigma 1 will be greater than sigma 0. If sigma 1 is greater than sigma 0, then e to the sigma 1 will also be greater than e to the sigma 0. And e to the sigma 1 is the radius of the point corresponding to this one in the z-plane. And e to the sigma 0 is the radius of this circle. So all points to the right of this line will map into points outside of this circle. Any point to the right of this line will have sigma 1 greater than sigma 0. Any point outside of this circle will have a distance e to the sigma 1, which is greater than e to the sigma 0. So right side, outside. Okay, same thing we can do here. We can pick a point here, any point, and let's call that sigma 2. Right? And as long as sigma 2 is less than sigma 0, e to the sigma 2 will be less than e to the sigma 0. Right? So if I have a point on this side of the line, on this side of this line, that'll get mapped to a point in the z-plane where the radius is less than e to the sigma 0. Radius is less than the circle corresponding to this vertical line. So any point on this side of the line will get mapped into points inside the circle. Outside, right side will get mapped to the right side of the circle, to the outside of the circle. Left side will get mapped to the inside of the circle. Okay. There is one special point that we should mention. If I go all the way out to minus infinity, right? Where does that point go to? If I go all the way out to minus infinity, well, that goes out to a point whose radius is e to the minus infinity. E to the minus infinity is 0. So infinity in the S-plane gets mapped into 0 in the Z-domain. Okay? If you remember, we had this thing in the Laplace domain. If I had a function which was finite and non-zero over a finite interval, then the Laplace transform of that was converged over the entire S-plane. In the Z-domain, though, it converged over the entire Z-domain except for z equals 0. And the reason for that is that we never really considered minus infinity when we talked about regions of convergence. And so let's suppose I have some x of s is equal to, say, e to the s, right? 3d to the s, just to make it different from this. Now, this thing, if I look at it the way we've been looking at it up till now, in the Laplace domain, doesn't have a pole because it doesn't blow up. But it doesn't blow up for all finite values of s, right? If I take, or let's take it, e to the minus s. Yeah. This doesn't blow up for any finite values of s. But if I take s to be minus infinity, then it does blow up. You know, if s is equal to minus infinity, I'll get 3e to the power infinity, and it will blow up, right? So when we say something doesn't have a pole, we mean it doesn't have a pole in the finite s-plane, but it might have a pole if we went all the way up to infinity, this thing might blow up. And that's why you'll get stuff where you'll say, yeah, it converges everywhere except for z equals 0, because this point actually corresponds to infinity in the s-plane. Okay. You don't have to think too much about it. Okay. So there's one particular line that we're very interested in the s-plane, and that's the j omega axis. Right? So here's sigma, here's j omega, and that's the one that we're really interested in. Because if j omega is included in the region of convergence, then we say we have a stable system. If j omega is not included in the region of convergence, we don't have a stable system. So where does this map into? Well, remember that the mapping that we have is z equals e to the s, which is equal to e to the sigma, e to the j omega. This line, the j omega axis, is where sigma is equal to 0. So if we plug in sigma equals 0, we get e to the power 0 being the radius. E to the power 0 is 1, and that's the unit circle. So the j omega axis maps into the unit circle. And it works, the unit circle, the circle of radius 1, works in exactly the same way in the z-plane as the j omega axis works in the s-domain. You know, if the j omega axis is part of the region of convergence, then you have a stable system. If the unit circle is part of the region of convergence, you have a stable system. And we can see that if we use our favorite thing. So a to the n u of n, we know that this is z over z minus a. And the magnitude of z has to be greater than a, right? If a is less than 1, if a is some point less than 1, I'm going to draw it here, but it could be anywhere with a magnitude less than 1. So if a is less than 1, then the region of convergence is going to be this. Right? And if a is less than 1, then think about what x of n is. X of n is a decaying sequence. Clearly, if I took the sum of the absolute values of x of n, I would get this is equal to summation absolute value of a to the n, which is going to be n equals 0 to infinity because of this u of n. So this would be 1 over 1 minus a. As long as magnitude of a is less than 1, as n goes to infinity, the second term will go to 0, and I'll get some kind of a constant. So this is clearly absolutely summable as long as a is less than 1. This sequence here is absolutely summable. And when I look at the z transform, I can see that the region of convergence for the z transform includes the unit circle. If I had, again, if this was 1 and if a was greater than 1, then I would get a sequence which kept increasing. Right? And as it keeps increasing, on this side, I would get a pole at z equals a. It's a right-sided sequence, so the region of convergence is outside of this, and it does not include the unit circle. So if the region of convergence includes the unit circle, you'll have a nice decaying function of some sort. If it does not include the unit circle, you won't. How could we have a greater than 1 and still have a stable system? Well, if you look at this on the other side, this thing decays on this side, right? On the left side. If I continued this on this side, I'd get a decaying function. So if I took x of n to be a to the n, u of minus n, let's take u of minus n, then in this case I have a left-sided sequence, and in this case the region of convergence would be inside of the circle, and that would include the unit circle, and therefore you can see that this thing is decaying, it doesn't blow up, you have a stable system. Okay, so unit circle is the same as the j omega axis in the Laplace domain. Okay, one last thing. The other way you can show this as well is, remember that x of z is summation x of n z to the minus n, right? And we can write z as re to the j omega. So this would be x of n re to the j omega to the n minus n. Or this would be, if I decided to evaluate this on the unit circle, then r would be 1, and I would get x of n e to the minus j omega n. But that's just the discrete time Fourier transform, x of e to the j omega. And the discrete time Fourier transform only exists for stable systems. Okay, so if I can do this, if r equals 1 is in the region of convergence, I can do that. If r equals 1 is not in the region of convergence, then this thing blows up for r equals 1, and therefore I can't. So if r equals 1 is in the region of convergence, r equals 1 is a unit circle. If that's in the region of convergence, then I can set it equal to 1, and I can find the discrete time Fourier transform, and I know that the discrete time Fourier transform only exists if the system is stable, and I'm assuming that this is the impulse response of the system. Okay, so that's another way of showing that you need the unit circle in the region of convergence. Now, one thing though, I'm mapping the j omega axis into the unit circle, but on the j omega axis, I can go from minus infinity to infinity, right? J omega axis, I can take any value of omega, any frequency I want. I can take 1 kilohertz, 2 kilohertz, 5 megahertz, I can go up to gigahertz, wherever I want. I can go all the way up to minus infinity and down, up to infinity and down to minus infinity. On the unit circle though, I go around and then I'm back in the same place. I go omega from 0 to 2 pi and I'm back in the same place. I just can't go more than that, right? And so we have a limitation here. We can only go from omega equals 0 to 2 pi here. Here we can go from minus infinity to infinity. What is the reason for that? Well, remember that this corresponds to a continuous time function. So if I looked at the Fourier transform of this continuous time function, you might have something like this. Let's say this is x of omega. This corresponds to a discrete time function. And if the discrete time function is, and we assume that the discrete time function is being generated by sampling the continuous time function. And if you think about it, if I sample a continuous time function, what happens in the frequency domain? I get replicas every sampling frequency. So I get a replica at omega sub s, I get another replica at omega 2 omega sub s, and the same in the other direction. So if I started at 0 frequency and I get something, and then I get to omega sub s and I start repeating myself. And I get to 2 omega sub s and I start repeating myself. Okay, so as far as the discrete function is concerned, all distinct values that I can get are between 0 and omega sub s. And that's what we have in this here too. We have this point here corresponds to the 0 frequency. And as we go around, as we get to 2 pi, this point here corresponds to the sampling frequency, whatever the sampling frequency was. If we were thinking in terms of hertz, then let's say I have a signal like your voice signal, I'm sampling that at 8,000 samples per second. Then when I'm here, here's the DC value. As I go around, by the time I come back here, this is 8,000 samples per second, or 8 kilohertz. Actually, what we're interested in is half the sampling frequency. So this point here will correspond to 4 kilohertz. If the sampling frequency, I shouldn't write that because that's not always the case. Depending on the sampling frequency, this point here will correspond to half the sampling frequency, right? So this point here will correspond to 0 hertz. This point here will correspond to f sub s over 2 hertz, where f sub s is the sampling frequency. Okay, and we'll use this fact when we try and design filters. So when we try and design filters, we need to know where to put poles and zeros. Remember that poles tend to amplify the signal, zeros tend to attenuate the signal. And so suppose I want to attenuate a 60 hertz signal. I need to know where 60 hertz is. Well, where 60 hertz is will depend on the sampling frequency. If the sampling frequency is, 240 samples per second, then this point will be 120 hertz and this point will be 60 hertz. If the sampling frequency is 120 samples per second, then this point will be 60 hertz. Right? The position of the frequency will depend on what the sampling frequency is. Okay, and we'll look at that much more later on. Okay, that's it. So the 3 things, we've done 3 things this time. We've looked at what happens with a two-sided function. So if I have a two-sided function, the region of convergence is between 2 circles. If you can read this. If I have, that was one thing we did. Then we looked at a mapping from the S domain into the Z domain, which was this, Z equals e to the S. And then we went through basically the same things. We said, if we have a right-sided function, we can show that in the Z domain, that will correspond to the right of a line. In the S plane, it will correspond to the right of a line. In the Z domain, it'll correspond to outside of a circle. If we have a left-sided function, continuous time function, in the S domain, it'll correspond to the left of a line. In the Z domain, it'll correspond to inside of a circle. So it's like, we took a line. If I have any line, I take that and I kind of, everything to this side of the line maps into the inside of the circle. Everything to this side of the line maps to the outside of the circle. Okay, and because I'm taking an infinite line and I'm mapping it into a finite length circle, the frequency axis, basically what you get is you get replicas of the Fourier transform of the original signal. You get replicas of that in this kind of sampled domain in terms of the discrete function. So the third thing was that if I want to write it as shorthand, pi corresponds to half the sampling frequency. Okay, and we will use this in order to label the unit circle as to which frequency each point corresponds to. Okay, that's why this thing is going to be very, very useful. Okay, that's all I have for now.